All right, conservation of angular momentum part 2, because that initial idea about conservation of angular momentum doesn't cover all of the ideas of conservation of angular momentum. So here we go. Let's say we're looking down, so it's a bird's eye view. And we're looking down at a merry-go-round, right? And so the merry-go-round has a constrained axis there at the center. And let's say we have a boy standing here at the axis of rotation. Actually, no, we'll even have the boy standing on the edge here, right? And then another kid who's over here. And let's say it's Dan and Abhinav. And they're playing catch with the ball. So here they are, and they're tossing the ball back and forth. I would actually be doing this in class if we had it. I have a big medicine ball in class, and we could play catch with it. And I have my little green rotating platform, but oh well. So let's say that Dan and Abhinav are throwing the medicine ball back and forth. Obviously, they're going to throw it very hard at each other because that's the dynamic, apparently, that they have. And so they're tossing that medicine ball back and forth. And Abhinav's on the merry-go-round for no particular reason. Why? Who knows, right? Who knows what Abhinav is thinking? But anyway, nothing's happening here, right? Throwing back and forth, back and forth, back and forth, back and forth. We wouldn't expect this merry-go-round to start rotating, or at least physically. Hopefully you would understand that it wouldn't start to rotate. Well, why? Well, here, when Dan throws the object and gets to Abhinav, Abhinav actually does exert a force on the merry-go-round due to the static friction between his feet and the merry-go-round. And that static friction force would act like this, and that clearly goes through the axis of rotation, so would not cause a torque. So, no big deal there. Now, let's talk about a more interesting situation now, where Abhinav is standing here, and Dan is standing here. And Dan throws the ball to Abhinav there, so with an initial velocity. So here we go. The ball would travel here, and Abhinav would catch it. And hopefully, if I asked you, well, what would happen to the merry-go-round, you would see that when Abhinav would catch this, the merry-go-round would start rotating clockwise, right? That's just sort of normal in our physical experience. Or you may have done this yourself. If the merry-go-round is at rest and you run and jump on the end here, that the merry-go-round would start rotating, right? But you jumped on here, nothing would happen. Hopefully that's within your physical experience. The question now is why? And this is where things get a little weird. So initially, you may say to yourself, well, Vaughn, you're talking about conservation of angular momentum. Initially, this object has linear momentum, right? It's going to have whatever the mass of the ball is times its initial velocity. Okay, actually, let me just make this VI for sake of argument, VI. So it has linear velocity, right? And has linear momentum. When it catches it, clearly the system finally has angular momentum. Well, I'm going to make the argument that even though this object is moving linearly, it has angular momentum, which is sort of really weird that linear objects moving linearly can have angular momentum. But go with me here. Because notice here, when Abhinav catches the ball, that ball exerts a force on Abhinav in this direction, right? And that ball, that force, would then cause a torque that causes the system to rotate. Simultaneously, when Abhinav catches the ball, he exerts a force to the left on the ball, right? All right, correct? To the left on the ball. What that's doing is it's slowing the ball down because Abhinav is speeding up until they meet a common speed. But, so there's torques on this system. Oh, so that must mean angular momentum is not conserved, right? Except that those torques are now internal if I consider the system to be Abhinav, the merry-go-round, and the ball, because the force on Abhinav causes a torque on Abhinav, but the force of Abhinav on the ball also causes a torque on the ball with respect to this point. So those two torques are internal to the system, right? Because they're Newton's third law pair. And therefore, that must mean the initial angular momentum is equal to the final angular momentum because I've met the condition for net external torques equal to 0. It's not here like in the last one where the torque was equal to 0. There are torques, but they're internal to the system because they're between the ball and Ivanov, and the ball. So that must mean then that this object moving linearly had an angular momentum. And that's sort of really weird to think about. Well, here finally, what is the final angular momentum? Well, it's whatever the final moment of inertia of the system is times omega, finally. But there must be another form of the equation of angular momentum for a point mass that is moving linearly to have angular momentum, okay? So here we go and do a little bit of work in order to figure that out. And once again, we're going to come back to the idea that there's analogs between things moving linearly and things moving rotationally. So we know P is equal to mv, okay? So let's look at torque. Torque. The basic definition of torque, if you remember, just to go back to the very beginning, was R cross F. That is the most fundamental definition of torque. It was a way of linking forces to the rotation if they were at some sort of R. Ooh, that sounds similar here, because notice here, if the line of action of the velocity goes through the axis of rotation, that did not cause a torque, but now, or cause this object to rotate. But now, since the line of action of this velocity did not go through the axis of rotation, it caused this thing to rotate, meaning that this thing must have had angular momentum initially. So we're going to use a very similar sort of idea there. If torque is equal to R cross F, what is L going to be equal to? Hopefully you see what I'm going for. It's equal to R cross P. So if I have a mass moving with linear momentum, it has angular momentum as long as the line of action of the velocity does not go through the axis of rotation, i.e. R has a value. Now, in the same way that we had torque was equal to R, or the magnitude of torque was RF, sine of the angle between R and F, the magnitude of L is also going to be equal to R P sine of theta, where theta is the angle between R and P. Now here, well, that's weird because if you think about it, oh no, like that R is different at all points. But then again, theta would be different at all these points. Oh, how did we get around this with torque? Well, we said that the magnitude of torque was equal to F times a lever arm distance, where a lever arm distance was the perpendicular distance between the line of action of the force and the axis of rotation. It's going to be very similar here. L is going to equal whatever that momentum is times a lever arm distance as well. In that case, here's that lever arm distance from the axis of rotation out to what the line of action of the velocity is. And just to make that a little bit simpler, the magnitude of L is equal to M magnitude of V, L perpendicular. You'll also see that written as magnitude of M, magnitude of L, magnitude of R, sine theta. Those are two alternate ways of writing that same equation. And this is going to be what gets placed over here because we have a linear object that's moving that causes this larger rigid rotating object to move. And so this would then be the mass of the ball, the initial velocity of the ball, L perpendicular. Now, notice here that this is magnitude. Omega, internally, I can plug in positive and negative signs for because it is itself a vector. That means that if I'm using this form of the equation, I need to impose directionality in that term. So if I say clockwise is positive, when I plug in for omega, I'd be plugging in a positive thing. But for this term, I need to either put a positive or a negative in front of it. Here, because I know that that would cause the object to rotate clockwise, I'm going to say it is positive and select that one sign there. So here's how I can do collision problems between linear moving objects and rotational objects. Now, how about the other things in terms of conservation laws? Well, angular momentum here is conserved because there are torques, but they're internal. But what about forces? So is the net external force on the system equal to 0? And someone's going to say, yeah, well, there's the force of Ivanov on the ball on Ivanov. That meets the condition. But remember, the merry-go-round is artificially constrained. There's a force on the merry-go-round that comes from something that's not the merry-go-round or Ivanov or the ball. So that's why the merry-go-round itself doesn't start to translate while Ivanov is on there. So linear momentum would not be conserved here because of the constraint on the merry-go-round. Is energy conserved? Well, the answer is no, because the force between Ivanov and the ball is non-conservative in nature. It's a contact force and it's not an elastic force. Therefore, there's going to be some energy that is lost in this translation because this is an inelastic collision at its heart, right? So we can analyze all those things. So we're going to do one more video for chapter 11 where we're going to talk about what happens in problems between objects where there isn't a constraint such that both angular momentum and linear momentum are conserved.